Hello, everyone. So today we have our own Zack Garza, who is going to speak about compact moduli of Enriques surfaces.
Okay. Thank you so much. Very glad to be able to talk about this today. Going to speak a little bit. So this is a report on some joint work from last fall, which we have in the publication process now. This is joint with Valerie Alexeev, my advisor, Philip Engel, and Lucas Schaffler. And it's up on archive now if you'd like to go see it. Right, so I'll be talking about modular spaces of Enriques surfaces. So I'll say more about what modular spaces are and what Enriques surfaces are. My goal for this talk, since it's a little bit more algebro-geometric in flavor, a lot more than some of the previous talks, is just to give you some ideas of what goes into what we proved. I'll say the statement of our sort of main theorem. And I just want to give you some insight into the combinatorial tools that we use. Ultimately, we reduce a very hard algebra geometric problem to many different problems that are combinatorial in nature. And I have lots of diagrams to share, so I just want to give you some insight into what's coming up. So the top diagram will describe for us degeneration of surfaces. I'll say more about that. One of the combinatorial tools we use is called integral-affine geometry, and these three diagrams here describe some kind of union of projective varieties that make up the central fiber of a degeneration. One of the main tools that we use are Coxeter diagrams, which generalize the Dynkin diagram theory from Lie algebras that you may have seen. They're a little bit more complicated. We get larger diagrams, but these are the main two that show up in our work. And then we have several more that are obtained by a theory called folding, which is a technique that we generalize from classical Lie theory to this setting of Coxeter diagrams. So I just want to motivate a little bit just the general idea of modular spaces. So I'll be working over the complex numbers. I'm a complex algebraic geometer. By M, I'll generally denote by M just some modular space. And by M bar, that will denote a compactification, a very particular one called the stable pair or KSBA compactification. So I'll say a lot more about what this is. This is in some sense a canonical, functorial construction you can use that gives you a nice quasi-projective variety. So let me start with sort of an impossible goal, something that, if it were solved, I would be very happy. I would like to think of the category of varieties over the complex numbers and give it some kind of topological structure. So I'd like maybe some homotopy theory on this category, such that I can talk about its connected components. And the notion of equivalence I'd like to use is something called birational equivalence. And my idea here is I'm imagining this to be, my category. The blob is my category of varieties. And in some sense, I'd like to chunk it up into blocks such that, in any given block, I have all of these orange dots, which are meant to be just all kinds of different varieties. But I would like some canonical representative of that equivalence class. And so within each block, I'd like this blue dot. I'd like to understand that such that everything else in this block maps to it by a birational morphism. And birational is sort of the right notion of equivalence if you're working in modular theory. So I'll say more about that. And so the idea is, can we find some canonical model for every birational equivalence class? And canonical, I'm leaving to be a vague, undefined term here. This is essentially the goal of the minimal model program. You'd hope that that canonical representative is in some sense minimal with some kind of ordering you can put on the category of varieties. You might hope that it's smooth or it has at least controlled singularities of some sort. You'd also maybe hope that it's geometrically tractable in some way, that it can be described with some geometric construction. Maybe you have actual equations for that thing. And this is the general idea of the minimal model program, is to try to construct such representatives. For those of you who look at such things, I can mention another way to formulate this problem is that you could take the K-theory of the category of varieties and ask an equivalent question about the K-naught of that category. So just the Grothendieck group up to cut and paste relations. And I would be asking a similar question: can I find a nice representative within each K-naught class? So birational morphisms, I want to motivate a little bit. The idea here is that a morphism between varieties will be birational if you can find some phi between open sets U in the source and V in the target, both open, And in the Zariski topology, open sets are very large. They are dense in the Zariski topology. And so this is a morphism on most of the variety. And you think of the complement of that open set as the boundary. And maybe you might like to sort of piecewise match up the boundary components to get a morphism on the entire variety. So the U is like the open set of the moduli space. This 1, 2, 3, 4 is like the boundary, and it emits some kind of stratification. And you might hope to match up, well, maybe this boundary stratum gets mapped to some other boundary stratum in a different compactification. Or maybe you have two compactifications of the same space and you want them to share an open dense subset, and you'd like to describe the boundary. So birational morphisms are the right tool to study this. And so a first step into this classification problem is asking, well, can we enumerate which ways smooth varieties degenerate into mildly singular ones? So we don't allow arbitrary singularities necessarily. We want some control on them. And there are many different types of singularities, log canonical, Kawamata log terminal, sort of many different ways of controlling the singularities. And so the strategy here is to construct moduli spaces of whatever varieties you're interested in, usually of a fixed dimension with some fixed numerical invariance. And the hard problem is to find something that's geometrically meaningful when you find a compactification. So you want the boundary of that moduli space to be modular in some sense, such that the surfaces appearing over the boundary really do represent limits of smooth surfaces. And then a further goal you might hope for is to stratify and classify that boundary in some combinatorial way. So some explicit way of just listing out what are the possible degenerations of surfaces. So this is just my cartoon picture. If you haven't seen or looked at moduli spaces much, the idea is I have a parameter space, M, such that every point in M corresponds to some kind of surface. So I guess I'm looking at a moduli space of Riemann surfaces of genus 2 in this particular case. And if I take a one parameter family, so a curve in the moduli space, I should get a family of surfaces, which I'm calling X here, such that as I go through the family, as I progress from 0 to t to what I'm calling infinity, the surfaces deform in some way, and then at the limit and at infinity, I get some kind of singular surface. And what you're supposed to imagine in this example is taking a homology cycle around that bit of genus in the two-hole torus and collapsing that cycle down to a point in this case. And so the way we study this over the complex numbers is you ask for a family over a disk, complex unit disk. And you kind of perform an inversion, t goes to 1 over t, so that t equals 0 corresponds to the thing you're getting at infinity. And so over the general fiber, over just some generic t, in our case, we're looking at so-called K3 surfaces, so you get some kind of smooth surface above that in the family. And what you sort of hope for in these cases, conjecturally for Calabi-Yau varieties of all sorts, of all dimensions, this should be the case, that if you look at a sort of maximal degeneration, you expect that the fiber over 0, so the limiting surface, you expect that to break up into some easily manageable combinatorial components. In this case, these will be toric varieties, which I'll say more about. So you hope that that's a union of some much simpler surfaces. So in general, you have many different choices of which compactification to take. The one that I work with the most is this KSBA compactification, the stable pair compactification. Other popular choices include GIT compactifications, so taking a variety and quotienting it by the action of a reductive group. Or now there's some theory to work with non-reductive groups. Another one we work with quite a lot is the Bailey-Burrell compactification. And a couple of other choices would be these toroidal compactifications and semi-toroidal compactifications. So these involve, there are many advantages and disadvantages to each choice. So the KSBA compactification is functorial. It has this geometrically meaningful boundary, but it's very difficult to describe that boundary. The GIT compactification, there's sort of a nice package framework for analyzing these things. They're a bit hard to construct in full generality. The Bailey-Burrell compactification is quite easy to construct in most cases. And it has the benefit of having a very combinatorial lattice theoretic theory. The disadvantage is that the boundary that you add on is very small in most cases. In our cases, you'll add on dimension 1 and dimension 2 components at most, but we're working with a 19 complex dimensional variety. So it's not a divisorial compactification, not a codimension 1 phenomenon. And then you have these toroidal and semi-toroidal compactifications, which involve the choice of some toric data, some fans, again, some combinatorial structure. Again, somewhat easy to describe what's on the boundary of these things. The disadvantage is that there are infinitely many choices. So you have to choose fans, you have to choose semi-fans, and there's no, in most cases, there's no canonical preferred choice for which one to take. And then, you can construct all of these, so you might ask, how do they compare? Which one is the right one to take? So I just want to say a little bit about how you should think about this Bailey-Burrell compactification, since this will show up a little bit later. The idea is I'm thinking of, so in this case, I have a moduli space of Enriques surfaces, so unpolarized. This is one of the spaces that appears in our work. And you imagine this space as some kind of open variety, which is missing a boundary. So here I have a boundary missing from that. And the compactification, the Bailey-Burrell compactification in this case, will involve adding on 2 points. So I have P1 and P2 here, and 2 curves, C1 and C2, respectively. And this is just sort of a cartoon of this situation. We'll have some other diagrams that describe this a little more accurately a bit later. But what happens in these Bailey-Burrell compactifications for us is that you end up adding points and modular curves with some level structure. So C1 and C2 or some gamma ends, or X ends or Y ends. So just to talk a little bit about some history of this work, we're looking at surfaces of Kodaira dimension 0. So there's a classification of surfaces that goes back to the early 1900s, late 1800s, due to the Italian geometers. You can generally break surfaces up by their Kodaira dimension. And in the surfaces case, you have so-called abelian surfaces, the K3 surfaces, Enriques surfaces, which is what we're working on. And there's another category called bielliptic surfaces. And compactifications for these, we're slowly progressing through them. A2, the moduli space of principally polarized abelian varieties, a nice compactification of this was constructed by my advisor, Alexeev, in around 2002. F2D, these are degree 2D polarized K3 surfaces, primitively polarized. And this is the subject of a lot of recent work, culminating in a compactification for F2D for all D, due to Alexeev-Engel in 2023. And so continuing this line of work, we're working with just the degree 2 numerically polarized Enriques surfaces and hoping to extend this to degree D numerically polarized. And the bielliptic surfaces are, as far as I know, still open. I don't believe there's a moduli space for these guys. So just some history here. The sort of canonical, the reference for these types of moduli spaces would be the Deligne-Mumford-Knudsen compactification of pointed stable curves. So this sort of serves as the template for the types of compactifications we're looking for. This can be described as a variety, the dimension can be described, the boundary is well understood, the cohomology is well understood now to some extent. And this is still an active area of research. So the hope would be to have a theory like the moduli space of curves for, let's say, just surfaces. And by the way, by surfaces, I mean complex surfaces. So these are real 4 manifolds, the complex 2 manifolds. So the line of work we're looking at with Enriques surfaces started, well, one could say it started with Enriques in just like 1903, somewhere around there. I'll say more about that. But at least the moduli space was first initially studied by Horikawa around 78, who looked at a certain so-called period domain and looked at what was more or less a GIT-style construction and studied a Torelli type map between the moduli space and the period domain, and sort of works with explicit equations and describes the possibilities for what those equations can be. Sturck, in his thesis in 91, was able to describe the Bailey-Burrell compactification of these degree 2 Enriques surfaces, and pioneered some the use of lattice theory in this classification of what the boundary looks like. So this involves a lot of lattice theory, Coxeter diagrams, and so-called cusp diagrams. And we'll see a few of those. As I said, Alexeev described the boundary of the moduli space of abelian varieties and discovered this sort of duality between Delaunay decomposition and a Voronoi decomposition. So this is kind of maybe a first instance of some view of mirror symmetry in these kinds of constructions, which inspires a lot of what goes on for the compactifications of K3s. Lucas Schaffler, one of my collaborators, described in his thesis a four-dimensional family of degree 6 polarized Enriques surfaces. And finally, in 23, there's a general theory for F2D that we leverage, so the moduli space of K3 surfaces. And it pioneers this theory of recognizable divisors, which allow us to construct these KSBA compactifications. And so I will just say it is hard to compare these moduli spaces. There have been entire papers written on them. For example, Luyenga looks at degree 2 K3 surfaces and compares the GIT and the Bailey-Burrell compactifications. Laza and O'Grady look at a moduli space F220. These are K3s with a generic Picard lattice 220, which is an invariant of these specific lattices. And that's a fairly recent paper, 2021. And so just the comparison problem here really is generally difficult. All right, so let me tell you what an Enriques surface is. So we're looking at varieties over the complex numbers, which are smooth, projective, two-dimensional, so they're surfaces. The main property is that the canonical bundle is non-trivial, so omega z is not isomorphic to O of z, but the second tensor power of the canonical is trivial. And so you can phrase this in terms of divisors. The canonical divisor is not numerically equivalent to 0, but twice that divisor is. We also need this additional property that this particular Hodge number, H01 of z, is 0. And another way to phrase this is that it's there's an invariant called the irregularity, the difference between the geometric and the arithmetic genus, and that should be 0. And just for edification, here's sort of what the Hodge diamond looks like. Most of the interesting action is happening in H2. If you haven't seen this before, right, this is a decomposition of the singular homology tensored up to C into parts I plus J, which sum to N for Hn. So this is a finer algebraic invariant that we use to study these surfaces. So there's a nice bit of history here, like where did these surfaces come from? Why is Enriques' name attached to them? There's a story recounted by Dolgachev that in the late 19th century, Enriques and Castelnuovo would walk through the arcades in Bologna in Italy, and they were trying to classify surfaces, and they wanted to discuss, well, if the irregularity and the genus, which is the second plurigenera, both vanish, can you conclude that X is birational to P2? In other words, is X a rational surface? And they wanted to know, well, so that turns out to be a true statement, that if those two invariants vanish, then you do have a rational surface. But can you eliminate this condition on P2 of X being 0, the second plurigenera? And that is true for curves, and it's natural to conjecture it might be true for surfaces as well. And so both Enriques and Castelnuovo came up with counterexamples where PG and Q are 0, but P2 is 1. But they're still Kodaira dimension 0, and they're not rational surfaces. And the way they prove this is not rational, maybe I'll skip over this. There's something called termination of adjunction, which holds when you're a rational surface, and they prove that this process doesn't terminate. So let me try to define for you an example of a construction of an Enriques surface. So we'll start with this variety P1 cross P1, so over the complex numbers. And let me define an involution in coordinates, which just negates the second coordinate on each of the P1 factors. And so you can think of this as xy goes to negative x, negative y. So this involution has 4 fixed points. So basically plus or minus, well, 0 in the first coordinate, infinity in the second coordinate, whatever choices you can make there. So you can explicitly describe the fixed points of this action. And now take a curve, which is in this particular linear system. So it's the anti-bicanonical linear system. which is tau invariant. So only those curves, so this turns out to be O of 4, 4, which are invariant under this involution. So this is a little bit convoluted, but I promise that this is a relatively straightforward construction once you sort of go to coordinates and work with polynomials. These are polynomials in a variable, let's say x0, y0 in green here for the first copy of P1 and x1, y1 for the second copy of P1, such that the total degree of those polynomials in each of the separate variables is 4. And then it's also invariant under this involution above. So here's just an example. You can see that all the green terms have total degree 4, all the blue terms have total degree 4, and you can mix them and match them in whatever way you like. So you have a curve in P1 cross P1, B, and you can take a 2-to-1 branch cover over that curve. And Horikawa, in one of his papers, shows that what you get is a K3 surface as that branch cover. And that involution on P1 cross P1 lifts to an involution on the K3 surface. It actually lifts to 2 involutions. So this is our original involution tau. The involution we want to take is this one, which negates all 3 coordinates. That one turns out to be fixed point free. And it's a theorem that if you have a K3 surface with a fixed point free involution, that the quotient of that is an Enriques surface. So we get some kind of diagram like this. We have P1 cross P1 down here. We have tau. We have a lift of tau, which I'm calling iota Enriques. And because omega z is 2 torsion, you get an tau 2-to-1 cover going to some surface z, which is x modulo this involution. And that can be shown to be an Enriques surface. So the main construction that we use, this is the diagram that appeared as far back as Kosek's paper in the 80s. Horikawa had something that's birational to this diagram. And in fact, many components of this diagram go all the way back to Enriques in a paper from 1906. And so what we would like to study is this top half, the quotient of the K3 yielding the Enriques surface. And we reduce it to something in the bottom half here. So we have P1 cross P1. And if you mod out by that involution, you get something called a quartic del Pezzo surface with very well understood singularities. And this diagram commutes. It's a pullback diagram. And what's really nice about this is that this is, like the top part of this diagram is something that happens in the world of complex geometry. It's what we really want to study and vary in moduli. It's a little bit difficult. This bottom part of the diagram is essentially toric in nature. So we can work with polytopes, polygons, and somehow the bottom half is more combinatorial, more amenable to explicit analysis. And so ultimately what we'll do is pick a curve in this del Pezzo and vary the coefficients of that curve, and that'll help us describe the moduli of the thing going on upstairs. So I want to say a brief word about toric varieties, since these end up being an important piece of the story. So if you haven't seen these before, the basic idea is that associated to a lattice, so you can just think of a vector space, Rn with Zn sitting inside of it. Well, they're all abstractly isomorphic to that. To a collection of integral vectors in that lattice. So here I've taken 0, 1, 1, 0, and -1, -1. You can form what are called cones. And this describes for you, in this case, this is the toric variety of P2. And it describes P2 as glued together from 3 affine varieties, which are the 3 hyperplanes at infinity. So dual to this cone picture in sigma, you can sort of take a dual polytope. So that's what I have over here on the right. And the main takeaway from this is that if I have a polytope, a polygon of some sort, then that describes for me a toric variety. But actually, it's a bit more. It describes for me a toric variety along with a particular line bundle on that variety. And that line bundle, if it's ample, will give us a projective embedding of that variety. So we can think of that thing as living in some Pn. So we're doing this in 3 dimensions now. This is just a copy of that diagram above, the pullback diagram. And the bottom picture is just toric. So this is the polytope for O of 4, 4, which describes P1 cross P1 with that particular line bundle. And if you take the double branch cover, what this is supposed to represent is, well, you get some polytope upstairs, which is a 3-dimensional polytope. And the branch cover gives you a K3 surface, which is a hypersurface living inside of that toric variety. And the quotient by that involution gives you, again, a hypersurface and a toric variety, which is this Enriques surface that we're studying. And instead of varying the coefficients of the Enriques surface to do moduli, we vary the coefficients of these curves downstairs. So what we'll do is take a curve that's in O(4,4), given by one of these polynomials. When you quotient by this involution going this way, one thing that you do is you take only the invariant monomials under that involution. If you remember, it was xy goes to -x, -y. So those are highlighted in blue here. And you also get 4 singularities of A1 type. And so you take a curve that doesn't pass through these singularities, that lives in this toric variety, and take the double branch cover of that to get your Enriques surface. So if you think about varying the moduli of that curve, what you get is so it's sort of a naive moduli space of Enriques surfaces, which is some open subset U of P12 modulo, so D4, the dihedral group 4 to 4, being the symmetries of this diagram up here. And there's also a torus action on that. And so you could construct this as sort of a GIT quotient. So we want to use this to study and classify the boundary of Fn2. And we're going to use the K3 cover and leverage this work of Alexeev-Engel from 2022 on compact moduli of FL, so lattice polarized K3 surfaces, which are equipped with so-called non-symplectic involution. The idea here is that for a K3 surface, you have a sort of a canonical choice of a symplectic form that lives in the Hodge decomposition, and it'll be non-symplectic if this involution's action on cohomology negates that symplectic form. And so there's a nice theory of taking the ramification locus of such involutions to use that as your stable pair compactification. So this Enriques involution turns out to be non-symplectic, but it has a problem, which is that it's fixed point free. So this theory of ramification divisors and non-symplectic involutions requires that ramification divisor to contain a curve of genus at least 2 in order to form this stable pair compactification. So we have to go looking for another involution on X, and we cook up one called a Del Pezzo involution, and we take the ramification divisor of that. So once you have all of this, you can arrive at our main theorem. And so what we prove is that if you look at the stable pair compactification, this is a modular geometric compactification that is isomorphic to a particular semi-toroidal compactification, which can be described combinatorially for a particular collection of semifans. And some of these are actual fans, which means this is sort of a finite type kind of statement. And some of these are strict semifans, which is kind of an infinite type situation. Moreover, we show that there is sort of a choice of canonical fans that you can choose, these Coxeter-Winberg fans, and that there's a dominant morphism if you take the associated semi-toroidal compactification onto the semi-toroidal compactification we have from above. So in some sense, we've related to a canonical toroidal, in fact, compactification, and then we show that there's an isomorphism with the stable pair compactification. And we use now this fact to describe the boundary of the stable pair compactification. So the main theory that goes into this is that we classify boundary in terms of these, what are called ADE, and then also types B and C surfaces. So I'll say more about that. And we find models for these degenerations. And the way the proof works, so I'll say some ingredients that go into this, but the sort of core idea is that you should embed this moduli of Enriques surfaces into some other known, well-understood moduli space and take its closure there. So we want something like a closed immersion into that space of stable pairs. And then you want to pull back the universal family and understand the fibers of that family and understand the Enriques involution on those fibers. And it turns out that, well, you can just take this because somehow to go from K3s to Enriques, we're quotienting by like a Z mod 2 kind of action. And you might hope that you can take all of the boundary data for the K3 surfaces and quotient everything by 2 and somehow get boundary data for the Enriques surfaces. And miraculously, this idea works once you play it out. So I just wanted to talk a little bit about some background for this, this folding procedure that we use. So we compare our KSBA compactification to some semi-toroidal compactification, and we use folding of Dynkin diagrams to sort of see this quotient by 2 at the level of combinatorics. So these are just the standard Dynkin diagrams, types A, B, C, D, E, F, and G2. So these classify semi-simple complex Lie algebras. And the theory that we use is that to every such Dynkin diagram, you can associate a toric variety. So this is a theory of 80 surfaces, which is used in Alexeev-Engel-22, goes back to some work by Alexeev and Allen-Thompson a few years ago. And so, for example, this defines for you some kind of polytope, and it's naturally associated with the Dynkin diagram A5 in some way. You can embed that diagram in that polytope. And similarly for E7, there's some way to embed that into a polytope, and then this polytope describes for you some kind of toric variety. So these will be the irreducible components of our degenerations. So the way the classical theory goes for folding is that you have these simply laced Dynkin diagrams, which are the ones that have only one edge in them. And you can get all of the Dynkin diagrams from the simply laced ones by quotienting by some automorphism of the diagram. So for example, I have a type A diagram here, which is just a string of nodes all connected by one edge. And there's a symmetry through the diagram straight through the center. And if you quotient, so really what's happening is that there's a lattice underlying this, and you're taking the invariant subspace of the lattice under this induced involution on the lattice. The root lattice you get is isomorphic to type Bn, in this case, B3. And I'll just mention that you can do this for, you can get type C from type D by folding a similar way. You can get type G by folding by a threefold, an order 3 automorphism. And there's just a general theory that works like that. And so we generalize this to Coxeter diagrams. So our things aren't really Dynkin diagrams. They're a bit more complicated. So this is one Coxeter diagram that shows up in the work that we do. And you might notice that there's a symmetry in this diagram, which is through this horizontal line. And if you quotient by this symmetry, turns out that you get exactly the Coxeter diagrams for the degree 2 Enriques surfaces. And this is this is sort of part of the classification work that we do, involves finding very specific subdiagrams of these Coxeter diagrams. These will correspond to certain degenerations. And it turns out you can get the ones downstairs by finding symmetric ones upstairs, and then quotienting by that flip through the horizontal line. So let me just briefly outline the proof for this, how the sort of story goes. So if you just have some general moduli space which is amenable to these techniques, the way this will go is that you should start with some lattice and look at the orthogonal group of that lattice and find some neat arithmetic subgroup. And these will be, if you've seen moduli theory before, often you set up moduli with a marking of some sort, and this arithmetic subgroup should be your change of marking group, something you want to quotient out by. And then you hope to find some isomorphism between the coarse space of the moduli space you started with and this so-called period domain, which is the classifying space of Hodge structures. And so in our cases, this will be what's called a type 4 Hermitian symmetric domain, which means that, well, it falls into a certain classification, and in particular, it admits a Bailey-Burrell compactification. You then try to prove that you can find some semifan such that when you take the KSBA compactification and you normalize it, that's isomorphic to some semi-toroidal compactification of this period domain, at least at the level of coarse spaces. And now you study this object, this classifying space of Hodge structures. There's a correspondence between the cusps of the Bailey-Burrell compactification and orbits of certain isotropic subspaces. So this is the orthogonal Grassmannian of that lattice. And so you look for completely isotropic subspaces, so just subspaces where your bilinear form restricts to 0. And so the points that you're adding, which we call zero cusps, will correspond to orbits of isotropic vectors. So the vector is just where v squared v dot v is equal to 0. And in our case, we'll have some modular curves, these one cusps, which will correspond to isotropic planes. So a plane generated by two isotropic vectors, which pair to 0. Because we're working with such high dimensional spaces, we can't really draw pictures of the boundaries or the open stratum of this kind of construction. So we turn to what are called cusp diagrams, which help capture the combinatorics of the boundary. So in general, this is some kind of giant simplicial complex, which captures all of the incidence relations of all of the components you add at the boundary. So in this case, we're looking at the Bailey-Burrell compactification of two Enriques numerically polarized surfaces. And the way these diagrams work is that a circle represents a point that you're adding in the boundary. So there are 5 total points. And a rectangle represents a curve that you're adding in the boundary. So there are 1, 2, 4, 5, 6, 7, 8, 9-ish curves. And you have an arrow going from a point to a curve if that point is contained in the closure of that curve. So this captures the incidence in the boundary. And so what we do is set up comparison morphisms to different moduli spaces and figure out how the boundary components map to each other. So somehow that's captured in all of this, all of the coloring and the markings and stuff here. I won't go into it in too much detail, but it involves doing some lattice theory, which ultimately boils down to some linear algebra over the integers, which is in some sense concrete, explicit, but of course, yeah, working over the integers is difficult in general, but it can be done in this case. So what you do now is you've found all of these zero cusps and one cusp that you have to add on by doing this lattice theoretic analysis. Now for each of these zero cusps that you've found, you should go and construct some hyperbolic lattice, and you'll be able to make a model of hyperbolic n space using this lattice. So here's just my picture of what this sort of looks like. There's some giant cone of vectors in this lattice. The ones on the boundary of this cone are the isotropic vectors, v squared equal to 0. The ones in the interior, the rays that pass through that, are the positive norm vectors. And if you projectivize this cone, you just take an equivalence class of rays going through this disk, and you'll get some model of hyperbolic space. And what you want to do now is produce some tessellation of that hyperbolic space. So here I've started with some polygon in Hn, and this is the fundamental domain of a group action, which is the Weil group of this root lattice. And you want to, in order to produce a toroidal or a semi-toroidal compactification, you have to produce a tiling of this hyperbolic space, which is invariant under a specific group action, namely that Weil group. And one way to do that is to cook it up so that that has to be the case by taking a fundamental domain and acting by the Weil group by reflecting over the walls of the polygon, and successively reflecting gives you a tessellation of that space, and it's invariant under the Weil group by construction. So there's a way to go from that Coxeter diagram we had before to the construction of this hyperbolic polygon. And now finally, what you do is you look at that Coxeter diagram, and there's a certain poset of elliptic and parabolic subdiagrams. So these are subdiagrams such that the bilinear form restricts to be positive definite or positive semi-definite. And to each point in this tessellation, so for example, pick some point in the fundamental domain here, or I guess I already have one here, this lambda, which is point here. We will assign some kind of degeneration of surfaces. And so let me just describe briefly how that goes. How do you assign to that lambda some degeneration of surfaces? So you start with the Coxeter diagram at that zero cusp. So in this case, this squarish one is the one we have. And you assign lengths L sub I to all of the nodes in that diagram. And those L sub i's will be the the dot product of that lambda that you chose, along with these alpha sub i's, which are the roots. So this entire diagram encodes a root system, so some particular choice of vectors in that lattice, and you want to compute the dot products with those. And as you vary that lambda, you'll get a varying collection of these L sub i's. And so these L sub i's we'll use as the lengths of certain vectors. So there's a way to take this diagram and produce a toric variety. So essentially we're taking, looks like 16 rays in this case in some lattice. And then there's some specific choice of vectors. So if you take the dual of those rays, you'll get some polygon. So that's what we have here. With some specific choices of vectors for each one of the L sub i's. And then the L sub i's will scale each vector in a prescribed way. And there's some linear condition on the LIs that you choose such that this polygon actually closes up. But in any case, as long as you satisfy that condition, then you get some polygon. What you do now is you take a triangulation of that polygon. So this is that 16-gon where I've completed it to a complete triangulation. So everything is broken into basis triangles of size 1/2. Sorry, jump through here. And there's this theory that goes back to Symington of, so the essential idea is that this polygon will be the base of a certain Lagrangian torus fibration. And there's a notion of Symington surgeries you can do to modify the fibers of that fibration. And so in this case, I'm doing 4 of these surgeries, which involve cutting a triangle out of one edge. And these introduce fibers with an I1 singularity into the fibration. And then you take 2 of these polygons, one of them with reversed orientation, and you glue them together. And since each one is homeomorphic to a disk, you're gluing 2 disks by their boundary, and you get a copy of S2. And so you get something that's what we call an integral-affine sphere, and it has a so-called charge of 24, as long as you cook it up in the right way. And so what does this have to do with degenerations? This is maybe a slightly more evocative picture of what you get. So it's supposed to be some piecewise linear S2, and there are a bunch of triangles, a bunch of lattice points on this sphere. And the idea is that if I fix a point in this triangulation, and I consider all of the vectors emanating from it, so I'm taking the star at that vertex, then I can take the dual of that to get some kind of polygon. And that polygon defines for me one projective toric variety. And then I just play the exact same game at a different vertex, maybe an adjacent one. Take the star at that vertex, and you'll get some kind of dual polygon again. And now the fact that these 2 polygons are glued along this common edge in the middle, so that edge happens to represent a curve inside of that toric variety. It says that you should take these 2 toric varieties and then glue them along that curve. And now if you think about doing that around the entire sphere, you get some combinatorial recipe for gluing together a whole bunch of toric varieties. So I'll skip over this section. It's a little bit too technical. Just in the last couple of minutes here, I just want to talk a little bit about some of the classification work that goes into this. So really this construction of these integral-affine spheres is part of it goes into the main theorem. This is sort of how you describe degenerations. You describe all the different ways that you can deform these spheres, and that describes for you all the different boundary strata of the KSBA compactification. And then it's a slightly different challenge to understand what is the induced involution on these spheres. So all of this is happening at the K3 level, but then you have to sort of quotient by 2 to get the Enriques ones. And it turns out that the induced involution will either be the involution on the sphere that just, if you think of a sphere embedded in R3 with XYZ coordinates, the involution Z goes to -Z, so swapping the hemispheres. The quotient by that is a disk. So you get a sort of a triangulated disk in some cases. The other involution that you get is the antipodal involution on the sphere, so you get a triangulated RP2. And so I just want to say that The way you describe all of these different integral-affine spheres is more or less by studying the subdiagram poset of these Coxeter diagrams, and you look for certain maximal ones, these maximal parabolics or elliptics. And I'll just mention that you can do this by hand. It's not the most impossible thing in the world, but it does get quite involved quite quickly. So what I'm looking at here is I'm enumerating all of the different subdiagrams that are admissible, and I'm trying to find ones that are included in other ones to find the maximal sort of subdiagrams. So for example, I start with this diagram and I realize, well, it's included in this diagram, and this diagram is included in this diagram, and that diagram is included in no other diagram. So the one at the top is one of these maximal diagrams. So you can do this by hand, but it gets out of hand pretty quickly. So this is something that we turn to like Sage Math to, we write up some code that can do this classification. There's a slight technicality here, which is that there are automorphisms of the diagram. So really you have to understand orbits of these maximal subdiagrams under the diagram automorphisms. So it gets a little complicated to code up, but it can be done purely in code. And so just with the last couple of minutes, I just want to talk about some things that I'm working on now and things that are hopefully some points for future work. So I'd like to sort of extend this to these bielliptic surfaces, which is the only thing missing in the Kodaira dimension 0 case. I don't know if similar combinatorial techniques will work to study these boundaries or construct these compactifications, but it would be nice to sort of close up the story and complete that case. And then, of course, the next line of work would be to work on kappa equals 1 and then kappa equals 2, 2 being the maximal Kodaira dimension for a surface, which we expect will need entirely different techniques. But that's right. We would like to have a complete classification of KSBA compactifications for all surfaces. What I'm working on now is if you have already a well-understood moduli space where you have all of this combinatorial boundary data, often these moduli spaces will have interesting divisors in them, codimension 1 subvarieties. And so you might hope that you can intersect the boundary data for the divisor with the entire space, or somehow restrict the boundary data for the entire space down to the divisor to describe a compactification for that smaller space. More generally, I'd like to work on just families inside of a moduli space, so higher codimension. And my current project studies cobal surfaces, which are a divisor in the Enriques surfaces. And I'm starting to look at something called Halfven surfaces, which are examples of elliptic fibrations. And the goal would be to describe KSBA compactifications for all of these. And just in case anyone's interested, there's some sort of far off ideas that I would like to sort of investigate at some point. So we worked with these cyclic Galois covers, which were Z mod 2 for the sort of Galois group of the cover. So I do wonder if some of this theory generalizes to higher order cyclic groups for Galois covers. You could also consider relative moduli spaces. So instead of looking at a moduli space of surfaces, you could look at moduli of maps of curves into surfaces or maps of surfaces into a fixed space, generalizing weighted stable pointed curves. And in the curves case, you have sort of a notion of things like Gromov-Witten theory and Donaldson-Thomas theory by doing intersection theory on these moduli spaces on the compactifications. So I would wonder if such compactifications can be constructed for surfaces. I'd like to see if you pass to a level structure cover, can you somehow relate the boundary data for the, if you have something like F2D where you understand it pretty well, and you pass to a level cover, can you understand the compactification of that cover? Similarly, it kind of, there's some cases where it seems like some of these techniques might generalize. So Calabi-Yau threefolds would be an interesting example. Again, for Calabi-Yaus, we expect the central fibers to be triangulations of spheres in general. Things like Kählers, hyperkählers, holomorphic symplectic manifolds, tropical varieties, Fano varieties. It's a big question to me whether or not the boundary of compactifications for these kinds of varieties can be understood in a combinatorial way. So there's a bit more here, but since I'm just about out of time. Maybe I'll just leave this up and say thank you so much.
Thank you very much. So is there any questions? You're welcome to just unmute or write in the chat. If you have.
So are you saying that the boundaries inside the modular spaces consist of all the maximal degenerations of the, like, quotient by the maximal degenerations of the K3 surfaces?
Yeah. So we have to look at the non-maximal ones as well. It turns out that there are 3 types of degenerations, which are kind of determined by the nilpotence index of the Picard-Lefschetz transform in a family. And so there's like types 1, 2, and 3, depending on if it's nilpotent of order 1, 2, or 3. Maximal ones are like type 3. And that's what this sort of classification work gets into. This is describing the type 3 degenerations. You look at sort of maximal parabolic subdiagrams. And then, yeah, the sort of moral of the story is that you can look for the maximal degenerations of K3s and then quotient them by the Enriques involution to get the maximal degenerations of Enriques surfaces. And that also works for the non-maximal ones as well.
I see. So the point is we know what the degeneration looks. We know what the general K3s look like, and then we try to quotient by similar too. So that's why you need to classify like what are the possible quotients.
That's exactly right. Yeah.
Which corresponds to the quotients of the diagrams.
Yeah. For the K3 surfaces, the main thing is we have these, the Coxeter diagrams, and then you have these integral-affine structures. And so the main hard part of this problem is finding K3s, for these integral-affine structures, you have to find very particularly symmetric ones. They have to emit 2 commuting involutions, one of them being the Enriques involution, the other one being this so-called Del Pezzo involution. And so they correspond to quotients of K3 sort of diagrams and integral-affine structures, but not just any such diagram. You have to find these especially symmetric ones, which emit 2 involutions.
I see.
And then you also have to understand the involution on the stable pairs, the involution on the so-called ADE surfaces. So that's why you get types B and C for the ADE classification. It's just because if you, for the K3 situation, you only have types A, D, and E, but then you can quotient, a type A surface to get a type B or a type C, for example.
I see.
Yeah, thank you for the question.
Perhaps we can stop the recording now.